Good evening, everybody. So, today we will start from the different electronic states which are arising from multi-electronic configurations, because we are trying to have these electronic states and we are looking for the corresponding electronic transitions. So, to know precisely what are those electronic transitions those are taking place from one particular level to the other, and for multi-electronic system we have seen that we have an electronic state where 2 p electrons are present or 2 d electrons are present. And in crystal field terminology, what we were talking about, that in an octahedral crystal field, these 2 electrons can be present either in the T2G level or in the EG level. So, what we see that during these electronic transitions, we can have electrons, both the 2 electrons in this T2G level, or these electrons can go up to the EG level. So, if there is any electronic transition which is being taking place, then we can find out the corresponding changes in energy which is taking place between these 2 states. So, we have the state number 1 and the state number 2, and we will be leveling according to the corresponding Russell-Sanders coupling what we have seen. Due to that coupling, we can find a particular state which can be defined nicely in terms of its corresponding spin values and the orbital momentum, orbital angular momentum values, and the corresponding spin orbit coupling values. So, these are the 3 quantities which can nicely explain or which can nicely define a particular state. And since we are going to apply the corresponding selection rules, so looking at this first stage, that means the corresponding spin multiplicity, and we know that for a particular type of transition involving these metal complexes, we can have certain states where this spin multiplicity or the total spin angular momentum value will not change. So, if we can have some one particular state, suppose this state is defined as 3F and this is the free ion value, the free ion electronic state, then we put that in octahedral field, and when we are putting this octahedral field, this can undergo certain splitting and we will have new levels for those states, and between those states we will be seeing the corresponding electronic transitions. So, how we can draw this depending upon 2 things, that if we just simply change the corresponding crystal field splitting strength, that means the corresponding delta octahedral value with respect to that of our energy, then how the energy of a corresponding state can change, that clearly tell us that in a particular situation when the crystal field strength is more, what we have seen in case of high spin and low spin compounds, that one particular level can have high energy and the other level can have the low energy, and at a particular crystal field strength we can have the transition, that means we will be getting the corresponding transitions which will be defined as the nu 1 or nu 2 transitions. So, today we will see that what we can draw the corresponding diagram for those transitions. So, that is known as the corresponding Orgel diagram. So, is a primitive one, is a very basic one compared to that of our other high level diagram which is known as the corresponding Tanabe-Sugano diagram. and in this particular case we will be just looking for correlation diagrams. So, these are basically correlation diagrams which can show the relative energies of the electronic terms in transition metal complexes. So, basically we will correlate with respect to the free ion terms. So, we will be having some electronic terms, and for a particular electronic configuration, say it is D2, D3 or D4, and when we have the corresponding metal complexes of D2, D3 and D4 electronic configurations, these electronic terms will be changing in a particular symmetry of the metal complex, and then we will find that those terms will be responsible for the corresponding electronic transitions. That means involving one particular ground electronic term and the other one which is the excited one. So, we basically go for the corresponding correlation diagram for the relative energies of the electronic terms, how the relative energies of these electronic terms will change. And Orgel diagrams are restricted to only show weak field, that is mostly we will be talking about the corresponding high spin complexes and offer no information about the strong field cases. So, it will be basically a very primitive diagram or very primitive correlation diagram involving the corresponding electronic states where we have only the corresponding weak field cases. That means, we do not have the strong field cases where we do not know what should be the energy of the corresponding term when we go for a very strong crystal field. Because these Orgel diagrams are qualitative, that is why we are talking is as a very primitive one, no energy calculations can be performed from these diagrams. So, if we want to calculate quantitatively, because for energy calculations when we find why we need these energy calculations, because when we get the corresponding electronic spectrum and we see that we have the absorption axis and the corresponding lambda axis. So, if we have the corresponding spectrum in this fashion, what we will find, we get the corresponding lambda values, and these values will be known as the corresponding lambda max values. This can be the corresponding lambda max 1, this can be lambda max 2 and this can be lambda max 3. And at the same time we will have their epsilon max values. So, these calculation of these lambda max values basically gives us some idea about the corresponding energy packet which is required for a particular electronic transition. And since Orgel diagrams are not very much quantitative, we cannot precisely calculate the corresponding energy values, but only thing that we can predict from there that what are the corresponding states or the electronic term symbols which are involved for the corresponding metal complexes, those are involved for a particular type of transition. So, we will be considering the nature of transitions, that means the states which are involved for those transitions. So, we will have the corresponding level for these states for the free ion or in the complex form, and then those states will be responsible for the corresponding transitions. So, we cannot have the corresponding precise calculations of the energies corresponding to these transitions, but they can show only the symmetry states of the highest spin multiplicity instead of all possible terms. Since we are talking about the high spin cases, so we will have the high spin multiplicity. So, the different symmetry states of the high spin multiplicity system for a particular electronic configurations, and how we can go for a corresponding splitting and the transitions. Suppose we have a simple P2 electronic configuration. So, there are different terms basically. So, if we can have say the corresponding octahedral complex and the corresponding electronic states we can have. So, we will have the different electronic states in our hand, and since it is a multi electronic configuration, we have more number of these electronic states, and we have the corresponding level for those electronic states. And in group theoretical terminology, these levels are nothing but their corresponding irreducible representation. These are their corresponding irreducible representations. Those representations which cannot be further reduced. That is why it is irreducible representations in the group theory table, character tables, we can get that. So, we have the corresponding S level, P level, D level, F, G, etc. levels. So, these levels basically can split in a particular say octahedral field in A, E and T terms. So, these are the basically the limit where we have this is singlet level, this is doublet level and this is the corresponding triplet level. And we cannot have anything which is beyond T, that means we cannot have the quartet level. So, we cannot have anything or any state which is higher than the threefold orbital degeneracy. So, this has the threefold orbital degeneracy. And that is basically the limit for that orbital degeneracy. So, what we find that for a situation where we have the P2 electronic configuration and which has the corresponding hole equivalent, that means the number of holes present in a corresponding closed system is equivalent to P4 also. So, in these two cases we can have the corresponding states like P, D and S. So, how we can get all these electronic states from the combination of the corresponding spin angular momentum and the orbital angular momentum, that we can see, because if we go for more complicated systems like D8 or D9, the situation will be much more having more number of these states. So, if we have the corresponding P2, we can have the total ML and the MS values corresponding to the total L value and the corresponding total S values. So, those we can find out, and from there we can go for a particular microstate table, and from the microstate table we can have the different combinations of ML and MS values, because a particular term will be defined by their individual ML and MS values. Then we can get the corresponding states, and states S, P, D having some spin multiplicity. So, these are the corresponding possibility what we can have, those are S, P and D level. So, depending upon the corresponding capital S, L values of 0, 1 and 2. So, if it is 0 it will be S, if it is 1 it will be P and if it is 2 it is D. Then we can have the corresponding terms. So, combination will give only the ground state as the corresponding triplet P level, then singlet D level and singlet S level. So, these are the three levels we can have. So, once we get this P, D and S level, we designate at about their corresponding spin multiplicity. This is 1D and this is 1S. That means, we can have the corresponding capital S value equal to 1, here the capital S value equal to 0 and here also capital S value equal to 0. That means, here we can have two unpaired spins, but here we have the paired spins. So, wherever we see the corresponding electronic transitions, we do not expect a corresponding electronic transition from this spin state to the other spin state, where spin multiplicity is changing. So, we have this term, and from there we just get that the ground state term should be the corresponding triplet state. So, 3p will be its corresponding term, which we can get for a p2 electronic configuration. Then we will see how this particular 3p term, when we put this in octahedral field, what will be its corresponding level for a particular p value. So, p has the corresponding value for this L, capital L is 1. So, we can have the corresponding multiplicity value equal to +1, 0 and -1. So, definitely once the state is p, we can immediately see it has the corresponding orbital degeneracy is of threefold. So, for other metal complexes, because we should not be happy with only the p2 electronic configuration at its corresponding term values, we should be happy with other electronic configuration. That means, at the same time we will be dealing with D1 to D10 electronic configuration to get these corresponding term symbols. So, if we have like P2, if we have D2, the D electrons have the corresponding ml values equal to 2. So, we can have the combination of these. So, there we get up to G level also. So, S, P, D and G and F also. So, we have these all these values, we can find it out for a D2 electron configuration. So, this triplet states, we have two triplet states, one is 3f and another is 3p, and then 1g, 1d and 1s levels, and which is also true for D8 electronic configuration. So, for 3 or more electrons, there is a long tedious process for determining these particular term symbols for the different electronic configurations. So, if we know the corresponding terms in various electronic configurations, so what we see there, that we have the different terms, that means those multiple terms of various electronic configuration. So, we see that we can find it out for P2, we can find it out for D2, or we can find it out simply for D1 and D9 system. For D1 and D9 system, we have the corresponding term as 2D, because we have only one unpaired electron. So, one unpaired electron is giving rise to a single half spin. So, the capital S is equal to half. So, how this particular term can split under the corresponding crystal field, and what is the corresponding terminology, what will change from there, and how we get these for the different electronic configurations. So, from D1, D2, D3 and more, we have these, but we can have the corresponding determinations in the tabulated form. What we will be using basically, because we will be interested to know the corresponding terms what we can have for a particular electronic configuration, and in the tabulated form we have all these values. So, this is a full form of these various electronic configurations, starting from, say, we can include also S2, P6 and D10, because when we have the corresponding electronic configurations for the field levels such as S2, P6 and D10, when all the orbitals are filled. So, we have a state where no other combination is permissible. So, we definitely have a singlet state. So, this clearly tells us that this will give rise to a corresponding singlet state, and since all are filled, so capital S is equal to 0. So, is a 1 S term. Similarly, for P1 and P5 we will have a corresponding 2P term, and next we have seen what should be for P2, what should be for P3 and for the different D levels. So, what we see for this D1, the configuration, the electronic configurations and its corresponding free ion terms in different D configurations. What we have seen just now for the D2 electronic configuration, the three free ion terms, what we have defined there for D2 is that 3F, 3P, then 1G, 1D and 1S. So, this is the corresponding ground state term. Similarly, for D2 we have the 3F and 3P, these are the values. For D3 we have 4F and 4P, and what we see that for D8, since it is the whole equivalent for D2, so for the D2 the corresponding terms for D2 are also applicable for D8, which is the corresponding nickel in +2 oxidation state. So, whenever we find the corresponding nickel complexes in this electronic configuration, we will utilizing the corresponding terms for D2. So, for nickel complex we will have the corresponding ground term as 3F. So, this 3F term for nickel complex can also be splitted under the corresponding crystal field, and the corresponding splitted terms we will just utilize for their corresponding transitions in different levels. So, these electronic terms will utilized, and these electronic terms will give rise to the spectral transitions and the corresponding spectra. So, these atomic electronic states, so these are the free atomic electronic states, how they can undergo splitting such that we can have the new terms in a particular symmetry. If it is an octahedral symmetry, so we will get the corresponding term such as the F term or P term or G term within the corresponding OH crystal field, such that we can have some important information related to that transitions. So, we can have the corresponding group theoretical analysis to term splitting, because we get those terms, but we cannot have the corresponding terminology for those terms which can have splitted to, say, when we have this S, P, D, F and G, we will have under the crystal field we have the A term, we have the E term and we have the T term. These are the corresponding splitted terms in the crystal field. So, these are the corresponding terms. So, once we have the term, and these particular terms what we can call as the irreducible representations, which are nothing but the corresponding terms in octahedral symmetry. So, if we put octahedral symmetry for this particular, these are the terms, so up to I basically, say S, P, D, F, G, H, I. So, these are the maximum limit what we can have here while handling D1 to D10 electronic configuration. So, if we have the S term and it has only one particular state, and that state can be designated within the octahedral field as A1G, which is also singlet, and it has some symmetry requirement for the labeling as 1, or in some cases it can be labeled as A2G. So, with respect to the C2 axis, if it is symmetric, we have the corresponding label as 1, and if it is symmetric with respect to inversion, it will be labeled with G. Since the field is corresponding field is octahedral crystal field having one center of symmetry, so all these states have been labeled as with G. But if we put those terms in tetrahedral field, tetrahedral crystal field, these G terms will not be there, like that of the splitting or T term into EG and T2G. The way we are talking about the splitting of the d orbitals, the 5 d orbitals, similarly the degeneracy of this d term, the atomic electronic state corresponding to this D term will also be splitted like this, that means one doublet and one triplet. So, 5 states will be divided into a doublet and a triplet. Similarly, this P term, which is a corresponding triplet one, will be termed in terms of the corresponding crystal field as T1G. So, we will find basically in some cases that if the ground state is F term, after splitting the corresponding terms in say the corresponding octahedral field will be A2G, T1G and T2G, and if it has another excited P term which we are getting in D2 electronic configuration also, which is also triplet F, 3F is the ground state, then the immediate excited state for that particular term is 3P. So, we will have 2 T1G terms. So, these will be precisely be labeled that this T1G term is originating from F term and this T1G term is originating from the P term. So, within bracket we will write this as T1G P, and this will be written as T1G simply because this is originating from the F, and the F term on the left hand side will also be shown. Now, we have, if we have G, the total number of states will be 2 into 4 plus 1 is equal to 9. So, the 9 states, how we can get those 9 states is equal to a singlet state, a doublet state and 2 triplet states. So, 3 plus 3 plus 2 plus 1 giving altogether 9 states. Then we have H, then the number of states is equal to 11. So, we have 3 plus 3 plus 3 9 plus 2 11, and if it is I, then the total number of states would be 13, and 13 we are getting like these 2 triplet, another triplet. So, 9 plus 2 11 plus 1 plus 1. So, these are the singlet. So, in all these cases some similarity we can have, whatever is the term, corresponding term, whether it is S or I, we can have only the A term, E term and the T term, that is singlet, doublet and the triplet cases. Beyond that we do not have anything which is degenerate beyond a triplet state. So, basically these states show the number of spin allowed transitions, because if we consider that only triplet to triplet transition is allowed or singlet to singlet transition is allowed, then basically the corresponding spin values of those terms can be identified, and we can put the corresponding arrow between those two terms for the corresponding electronic transitions. And with those allowed transitions we can have the corresponding respective symmetry designations also, whether it is A1G or A2G, because they have two different symmetry levels. So, the qualitative diagram, the qualitative correlation diagram what we are getting in terms of the corresponding Orgel diagram, the free ion terms, the P, D and F, we are calling these as the corresponding parent terms because they are originating from the free ions in presence of no ligand field, because the free ion we are talking about only the metal ion. That means, we are only talking in terms of the nickel 2 plus or cobalt 2 plus or iron 2 plus without the presence of the corresponding ligand field. So, that is why we have the corresponding term as the free ion term. So, this can be located at the center of the diagram. So, center of the diagram will be putting this particular these terms, and with the terms due to that electronic configuration in a ligand field on each side. So, if we are getting a D term for two different types of electronic configuration, we will put D, and on the left hand we will have one type of splitting, and on the right we can have the another type of splitting if it is originating from the D term. So, there are two Orgel diagrams basically we can have, one for D1, D4, D6 and D9 configurations, D1 and its whole equivalent D9 and D4 and its whole equivalent D6, because for D1 and D9 and D4 and D6 we have the corresponding ground terms which are same, those are basically the D terms. Similarly, for D2 and its whole equivalent D7 and D3 and D2 and its whole equivalent D8 and D3 and its whole equivalent D7 are also can be paired up. So, if we have the D2 D8 configuration, D2 D8, we have the corresponding ground term as 3F. Similarly, if we have the D3 D7, the ground term is again F, but of different spin multiplicity. So, we will be dealing with only the D term and the F term. Only difference for these different electronic configuration is that they are different spin multiplicity. So, altogether in this diagram, in these two diagrams, we will be handling 4 plus 4, 8 different electronic configurations. So, out of 9 electronic configurations, we will be handling 8 together. Only odd man out is the corresponding D5 electronic configuration, which cannot be handled by this diagram, because this D5 situation is little bit complicated and it can have two different situations like that of our high spin configuration and the low spin configuration. So, we will be handling if it is D1, D9 and D4, D6 electronic configuration with a D term. So, we will have for these qualitative aspects or qualitative picture what we can have. So, qualitative correlation diagrams we can draw, and those diagrams basically we are calling them as Orgel diagram. And here we are just looking for a particular term, how we are getting those terms, and those are basically the corresponding free ion terms, where no ligand is present. So, we do not have any ligand around these metal ions. So, this particular term is for D1 and D9 situation. This D term we are getting, and then the corresponding one will be getting for the other one, that means D4 and D6. These are their corresponding whole equivalent. So, that means they are also pairwise, they are related. If we know about D1, you will immediately you can say that no, the other one will also be D9. Similarly, these two are the corresponding D4 and D6. Similarly, for F we can have the corresponding D2, the next one D1 and then D2, D2 and D8, and for this is D3 and D7, the next two are. So, here also we have the corresponding generation for the whole equivalents and the F term. So, how these two terms basically can split in terms of its corresponding crystal field. So, if we have the crystal field for these two terms, how these two terms can be splitted. So, in one such diagram where we have the F D term for these first 4 ions, and we will be getting this for one is for the D1 electronic configuration and its whole equivalent, in another case it will be for the D4 and D6 electronic configuration. So, only thing is and only difference is that the doublet and the triplet, these are the two cases. So, D will be like the D orbitals can be splitted into E and T2. So, D will be splitted into E and T2. So, in one case E will be the ground state, in another case T2 will be the excited state. So, in other case the triplet is the ground state and the doublet is the excited state. So, this is the two different cases. So, that means we have the D term, and Orgel diagram tells us that how this D term will be splitted in these two different electronic configurations and this corresponding splitting. So, for D1 and D9 and D4 and D6 we can have, so they have the corresponding equivalence, that means D1 will be equivalent to D6 and D4 will be equivalent to D9 for in terms of the corresponding splitting. So, we can have these 4 ions, that means D1, D9 and D4, D6, and we can have the corresponding energy values in this particular axis, and this D4, D9 they are equivalent. So, D4, D9 on the left hand side and D1, D6 on the right hand side, and again we see that there is a relationship between the splitting of the octahedral field with respect to the tetrahedral field because of the orientation of the different orbitals, what we have seen earlier, that in case of octahedral splitting, if we can have the corresponding 5 orbitals we have, and these are being splitted in a triplet and in a doublet form in an octahedral field, and this is the corresponding T2G set and this is the EG set, because of the relative orientation of the different orbitals belonging to the T2G set and other orbitals which are belonging to the EG set, and they are facing differently those orbitals towards that of our ligand field. So, if we go from an octahedral field to a tetrahedral field, we will see that the splitting is opposite. So, we will have the E set as the ground state and the T2 set as the excited state. So, same thing is happening when we have, instead of these are say 3D levels. So, these are 3D levels. So, these are the d orbitals. Now, instead of d orbitals, if we have the d states. So, they have the similarity. So, if these are the octahedral one, then the other one will be in the tetrahedral field of the different electronic configurations on the left and on the right. So, we will be plotting this energy with respect to the corresponding ligand field strength. So, energy in this axis and ligand field strength in the x axis, and the corresponding term, the term what we will be utilizing for the splitting. This can come as the corresponding term over here, and this is our D term. So, D will be splitted for D4 and D9 system in the octahedral field as EG as the ground state and T2G as the excited state, or E as the ground state for D1 and D6 tetrahedral, or T2 as the excited state when G subscript is missing for tetrahedral symmetry. Similarly, on the right hand, the D will be splitting in the opposite fashion. In opposite fashion, what the splitting is for octahedral, it is D1 and D6. So, T2G will be the ground state and EG will be the excited state. So, this is for the similar d orbitals, what we find that the T2G is the ground state and EG is the excited state, and without the G subscript we have the corresponding levels for the tetrahedral field. Now, we see that the second one for the F term. So, if we have these F terms, which is for the D2 and D8 and D3 and D7, we will be generating the corresponding F term, and F term what we have seen that a particular F term, when it is being placed in a crystal field, it will be splitted into, say if it is placed in an octahedral crystal field. So, it will be splitted into T1G plus T2G plus A2G, and these G subscripts are basically for the octahedral symmetry because I is present, and we will drop these G subscripts when we will be talking in terms of the corresponding tetrahedral symmetry. So, whenever we have the F term, whether it is in for D2 or D8 electronic configuration or D3 or D7 electronic configuration, they will have the corresponding splitting. So, again like the splitting of these D levels what we have seen on the left and on the right, similarly here we will have the splitting on the 3 levels on the left and splitting in 3 levels on the right also. So, we have this delta value. So, this F term is being splitted for A2, T2 and T1 on the left, and the reverse, that means T1, T2 and A2 on the right. And at the same time, whenever we have a F term, another P term is also there, which is the excited state, the first excited state in case of this corresponding D2 and D8 electronic configurations. What we have seen that 3F term is the corresponding ground state term and its first or immediate excited state is the corresponding 3P term. Similarly, for D3 and D7 electronic configuration, the 4F term is the ground state term and 4P is the first excited state immediately after this particular term. So, with respect to these delta values, the P term will also change its energy like this with respect to this corresponding transformations from T1 on the left and T1 on the right. Only difference is that here it is not crossing any of the terms. That means these two particular terms, these two T1 terms are basically repelling each other. These two are also repelling each other. So, they do not have any such crossing, but this T1 term can cross this A2 term. So, what is happening there at this particular lambda value, delta value, that means this particular crystal field value is therefore crucial and above which we have a corresponding crossover, because before this particular crystal field we have the A2 is the ground state and T1P is the excited state, but after this when the delta value is high we have the T1P is the ground state and A2 is the excited state. So, what we find in this diagram is that in an Orgel diagram the lines with the same RS term will diverge due to the non-crossing rule. Since they are not able to cross in some positions, so we have the non-crossing rule, but all other lines will be basically linear. So, these two basically are deviating from the linearity because we have the T1 term. So, the lines for T1, one is originating from the P term and another is originating from the F term. So, they basically diverge due to non-crossing rule because they will not cross. So, they will repel each other and they will just have the divergence. But the other lines in Orgel diagram, what we will find that other line, that means the line for T2 and the line for A2, these two are linear. So, we will have the linear line as well as the bend line in this particular diagram. So, we get this particular situation for all four, that means D2, D3, D7 and D8, where we have this F term what we have seen just now, and since this is not crossing and the red line is the corresponding critical line which will designate as the weak field case and the strong field case. So, in all octahedral situation these will all be labeled as G, and in tetrahedral situation they are all simply labeled as A2, T2 etc. Similarly, on the right hand side we have the G leveling and the non-G leveling, and these two things, that means what we can have for the P and F term, if these are the two horizontal line we can draw. So, that this is deviating from the horizontal line, it is coming down and reaching P and then again it is deviating. Similarly, when F is splitting for this T1, so it is going up, but it is deviating this particular value, and this T is basically simply deviating from this horizontal line. So, these are basically the levels depending upon the corresponding electronic configuration. So, if we have a D3 and D8 electronic configuration for the different situation where we have the F term, we can simply say that we can have the transitions from A2G to T2G, A2G to T1G and A2G to T1GP. So, these are the three basic transitions what we will see that in electronic spectrum we will find 1, 2 and 3 transitions involving these diagrams which we can predict from simple Orgel diagram. So, for a case of D2, what we will find that in case of this D2 electronic configuration, what we have seen that we can have 5 different states and 5 different terms due to the corresponding Russell-Saunders coupling. We can have 2 triplet states and 3 singlet states, and among these 2 triplet states which are 3F and 3P, we have the 3F as the ground state and the immediate excited state is the 3P and all other. Then what we can go for this corresponding correlation diagram, because we are slowly approaching from this diagram for Tanabe-Sugano to the Orgel to the Tanabe-Sugano diagram. So, we were talking in terms of the corresponding Orgel 1, so next we will just proceeding towards the goal where we will find that how Orgel diagram can give us some informations about to draw for some other correlation diagram which is Tanabe-Sugano diagram. Or TS diagram. So, Tanabe-Sugano diagram. So, this diagram basically will tell us that this is also a spectral correlation diagram, spectral correlation diagram. And this particular one is very much useful in the interpretation of the electronic spectra. So, we are still with the interpretation of the different electronic spectra of the coordination compounds So, these electronic spectra of the coordination compounds when we are having, so how we can interpret. So, interpretation is very much important. How we can go to their interpretation basically, and that gives us some important. So, apart from this diagram what we have found in case of the Orgel diagram, so we have seen that a particular state whether it is D or F in this diagram, in this Orgel diagram, and when this particular state is getting splitted, we have the corresponding term, that means if the F is giving rise to 3 terms which is A, T and T, one is T2, another is T1 and another is A2. So, these are the 3 terms we are having, and if we see that the energy, how the energy of this particular T1 term will change with respect to the strength of increasing crystal field. So, as we change this, we just basically see that it is going down to down as we go towards and some infinitely strong crystal field strength. So, this is not basically going towards the corresponding thing, that is go down and down, but in this particular diagram, which is different from this Orgel diagram, in the basis of that identification, that this particular one, the lowest energy state, which is very important, that means whether our lowest energy state is 3 T1 G. If this is the lowest energy state, then we will have the transitions from this state. This state we will be talking about the different transitions. So, depending upon its corresponding value for this transition, we try to have this as a typical horizontal line instead of this sloped line. Line with some slope can be converted to some horizontal line. So, this lowest energy state is basically plotted along the horizontal axis. That gives us our TS diagram. So, how we get these correlations, that we can find out from this diagram simply. So, for D2 electronic configurations, we have found out that we have 3F, 3P, 1D, 1G and 1 is electronic states. And interestingly, in terms of the energy values of these free ion terms, this 3P term, though it is a triplet state, it has higher energy compared to its 1D term. So, F is the ground state, then D, then P, then G and S. And we all know that F can undergo splitting in terms of its irreducible representation in OH crystal field or OH symmetry, the group theoretical symbol or the notation. We can get the corresponding irreducible representations of this particular 3F values in terms of the 3A2G, 3T2G and 3T1G. Similarly, these are the corresponding free ion terms, and due to these weak interactions we can have very weak splitting or the terms what we get from here to there. And since this is F term and we all know that F can be splitted in terms of the 2 triplet and 1 singlet, that means the total number of term value is equal to 7. Similarly, D into 2 terms E and T, 1 triplet and 1 doublet, P will remain as again a triplet term, G can be splitted in these values and S can remain as the corresponding 1A1G term. So, how we correlate this particular thing is that in strong interaction case, what we can have in the strong interaction state, we have the corresponding values as the corresponding electronic configurations what we can have in our hand as the T2G, the T2G EG and the corresponding EG2 electronic configuration. So, what we have that if we have the 3F term which is true for say vanadium 3 plus, which is a D2 electronic configuration. So, this 7-fold orbital degeneracy which will not be present in this particular form and that cannot persist in the octahedral crystal field. So, it will split into 3 new electronic states. So, these are the 3 new electronic states we can generate from the free ion 3F term, and therefore, after the splitting we have the corresponding states where the 3T1G has 3-fold orbital degeneracy as well as 3-fold spin degeneracy. Similarly, this also will have the same and this has 1-fold orbital degeneracy, but having 3-fold spin degeneracy. So, altogether if we consider this 3F term, we have this 3F which is splitting into 3 and this splitting gives us 3T1G, 3T2G and 3A2G terms. So, the spin is 3-fold but the orbital here is threefold, this is threefold and this is one fold. So, altogether we have 3, 3, 1, 7 into 3. So, 7 into 3 is equal to 21 total microstates we can get out of this particular term. So, in D2 electronic configuration we have altogether 45 microstates. So, only this particular term, the 3F term, can account for these 21 microstates, and we will be considering these microstates nicely for these transitions in this Tanabe-Sugano diagram, where we see that the triplet degenerate levels are most important for these transitions. So, next day we will still continue with this diagram for these actual transitions with those electronic spectra. Thank you very much.